Hello. So in this final series of screencasts, what we're going to do is move towards complexity. We're going to bring together all of the concepts that we've met previously and see how seamlessly they work together to allow us to understand and predict what some complex molecules are going to do. And once again, we're not going to be learning the complexity, we're going to be working the complexity out from first principles. So to start this process, we need to define a key principle, and that is chemoselectivity. What do we mean by the chemoselectivity of a molecule? Well, chemoselectivity is where one potential reactive site reacts in preference to other possibilities. Chemoselectivity is where one potential reactive site reacts in preference to other possibilities. And in order to work out this chemoselectivity, because it's clearly really important to understand a complex molecule, we're going to use electronic effects to predict what kinds of functional group are the most reactive. And we've started this process already with the simple basic rules of mechanism. Because in our simple basic rules of mechanism, we said that for nucleophiles, electron-rich things, the starting point of most mechanisms, we would prefer to have a negative charge over a lone pair, and we would prefer to have a lone pair over a multiple bond. And that is a very basic type of chemoselectivity. What about if we have to consider more subtle differences between reactive groups? And we're going to do this as a series of tests to see if you can work them out. And then after each one, I'll walk you through the right answer. So the first question, we have two anions. They both have a negative charge. How would we know which was more reactive, which was more nucleophilic? Is it the one on the left or the one on the right? What do you think? Hopefully, you said that the answer is the one on the right. That's the correct answer. Why is it more nucleophilic? The system on the right has a plus I inductive effect, pushing electron density towards the negative charge, making it more negative. The one on the left, that negative charge is delocalized into the aromatic ring, which is having a minus M effect, spreading out the charge. Spreads out the charge. So it's less negative, it's less available to attack. So this one is the more reactive one because it has the charge build up ready to attack. So that one's quite straightforward. Now let's think about chloride or iodide. Which of those do you think is the better nucleophile? I bet a lot of you said chloride and got the answer wrong. It's slightly counterintuitive and we have to understand why. Chloride is quite a small anion. Iodide is a much larger anion. But they have very different electronegativities. Chloride holds on to its electrons more. Iodide is less electronegative. It's more polarizable. And that means it makes bonds better. it can give away its negative charge more effectively, and that makes it more reactive. So perhaps a surprising outcome there. So it's about having that build-up of negative charge ready to go, but not holding it on too much because of your electronegativity. You've got to be prepared to share the negative charge that you've got with the thing you're going to react with. These kinds of arguments don't just apply to comparing different negative charges. We can think about comparing different lone pairs. So test 3. Which of these NH2 groups is the most nucleophilic? Hopefully you got that one right, and you said that the one on the right was more reactive than the one on the left. The reason for that? Very similar to test 1. Here we have a plus I effect donating to that lone pair, making it more electron rich. In this case, the lone pair is delocalized by resonance. There's a minus M effect from that carbonyl group. We can, in fact, draw a resonance form. We'll do it this time. O minus NH2 plus, and a double bond in there, where the amine has actually lost its lone pair altogether. And so that minus M effect makes this less electron rich. And therefore the more electron rich one over here is more reactive. Amines are more nucleophilic than amides. Test 4. Which site is more nucleophilic? OH or NH2? Vote now. Again, I bet this is one that some of you got wrong. I bet some of you thought the oxygen was more reactive here. First of all, let's remember, they both have lone pairs, but oxygen has a slight problem. Oxygen is more electronegative. And because it's more electronegative, it holds on to those electrons. Oxygen holds on to electrons. And it won't donate them so easily. It is nucleophilic, don't get me wrong, it will donate them, but not as much as nitrogen. Nitrogen is less electronegative, and it donates electrons better. And that means it's more reactive. So an amine is more nucleophilic than an alcohol when they're both neutral and reacting through their lone pairs. They are both nucleophilic, but this one is better. Test 5. Now, which of these amines is the better nucleophile? Hopefully, you felt this one was the better nucleophile. This system, with 3 hydrogens attached, is small. This system with 3 ethyl groups attached is large. And the small thing is better able to attack a crowded C delta plus. So ammonia would be more nucleophilic than triethyl amine. So that's thinking about lone pairs. What if we think about multiple bonds? Which of these will be most reactive and least reactive towards an electrophile, E plus. So remember what that reaction is. We're thinking about a pair of electrons moving towards an E plus electrophile. Vote now. Hopefully, you decided that this one on the left was the most reactive. Why? A plus M effect donates electrons to the ring. It's more electron rich. So it's more reactive. Here, we just have a plus I effect, and as we said in an earlier screencast, plus I effects are less important than plus M effects. The chlorine mainly has a minus I effect, so that begins to pull electron density away from the ring, and in the case of this nitro group, it really pulls electron density away from the ring. It's a minus M effect. It removes electrons from ring. That means it's less electron rich. That means it's the least reactive. So electronic effects, electronegativities, inductive effects, mesomeric effects, resonance, they control the chemoselectivities between is this negative charge more reactive or this negative charge, this lone pair or that lone pair, this double bond or that double bond. And that's how we begin to work on more subtle problems. There's one for you to look at here. This is part of the synthesis of one of the most significant drugs of the late 20th century, Viagra, which is a drug for erectile dysfunction. And all I'm asking you to do is to draw the curly arrows for the mechanism and to think about the chemoselectivity of that process. Why does the specific part of the molecule, the amine that you use, react with the acid chloride rather than other parts of the molecules? So try and draw a curly arrow mechanism, the initial curly arrows, and think about the chemoselectivity in that synthesis of Viagra. So it's not just comparisons between nucleophiles that we can make. We can compare between electrophiles and think about their reactivity using exactly the same approach. So if we have a set of different carbonyl compounds, we can think, to compare them, we consider how delta plus, the carbon, oxygen, delta plus, delta minus is. So we need to understand how delta plus that carbon is. And we can organize these compounds from the most reactive to the least reactive. And I'm going to talk you through that. The one on the left is the most reactive. We have a minus I effect of the chlorine pulling electron density away from that carbon, making it more delta plus. Here in the aldehyde functional group, remember we show the hydrogen on an aldehyde, there's no real inductive mesomeric effects to talk about. When we get to having methyl group on here, a ketone, there's now a plus I inductive effect. What that's doing is pushing electron density towards the carbon, making it less delta plus, less reactive towards a nucleophile. This ester over here, we have a plus M effect, which will be bigger than a plus I effect. So even less delta plus on the carbon. And by the time we get to the amide, the lone pair pushes in, and this is now a strong plus M effect. Why is it a strong plus M effect? N is a better donor than oxygen. Remember we said that when we're thinking about nucleophiles, the nitrogen is less electronegative, it wants to give away its electrons more, so this mesomeric effect, this resonance form, is stronger than this resonance form. The oxygen still more holds on to its electrons than the nitrogen does. And so this one over here is the least delta plus. So if we exposed all of these to nucleophiles, the most reactive would be this one, the nucleophile attacking the C delta plus of the carbonyl. We can think about doing this in an example. This is the kind of thing I could set as an exam question, showing the curly arrow mechanism, predict the outcome of the following chemoselective reaction. In the first step of the reaction, we're going to use H minus, that's what we're told to do, and we have a choice. We have a delta plus here and a delta plus here. The one on the left is a ketone, the one on the right is an ester. We've just said that ketones are more reactive than esters because the ester has a plus M resonance form that's pushing electrons already towards that carbon delta plus. That means the H minus will more attack the ketone. And of course the electron density has to end up somewhere good. That will be on the electronegative atom following the basic rules of mechanism. So we're using the basic rules of mechanism, start on the negative charge, move it to a delta plus, flow the electrons somewhere good. It's just we had to apply a chemoselectivity choice in our decision making. If we draw out the product of that, what we have is a bond to the hydrogen formed where that arrow is. That's what the arrow means. We've broken the double bond to oxygen, turning it into a single bond, and we've moved the electrons onto the oxygen. We're then told that step 2 of this process is to use H+. How do we work out the mechanism? We find the biggest source of electrons, negative charge, and we move it to a positive charge, and we have a really good one, H+. So we're making a bond between the oxygen and the hydrogen. And if we draw out the product of that, then we've made an OH here. There is, of course, still a hydrogen attached here, but because it's a hydrogen on a carbon, I'm not showing it at the end. What have we done overall in this reaction? We've turned a ketone into an alcohol. Remember, in an earlier screencast, we talked about the idea of functional group level. We've turned a ketone, which is functional group level 2, into an alcohol, which is functional group level 1. So the reaction process that we're doing here is a reduction of a ketone to an alcohol. Earlier on in the lecture course, I said I'm not going to teach you to learn what reducing agents we use or what oxidizing agents we use to go the other way. But what you can see here is that being given one and being told what it is, we can simply work out the mechanism in terms of curly arrows. This is the power of the mechanistic method. The final thing that we can predict, that I'm not going to talk very much about because you have a whole course on acids and bases, is which sites are the most acidic and which sites are the most basic. Generally speaking, acidic sites will generate a stable conjugate base. When you've deprotonated them, they make something stable. Maybe they have negative charges on electronegative atoms. Maybe they have products stabilized by resonance. The most basic site in a molecule will be the one that has the greatest electron density and can donate it to a proton. So you want your lone pairs or negative charges to be localized. And again, less electronegative atoms can more easily donate their electron density. It's a bit like the arguments about nucleophiles. And we're going to just look at one example of a molecule to see how we can predict that out. This is serotonin. It's a really important molecule in your brain, and it's associated with feeling euphoric. It makes you feel really good, it makes you feel in love, it makes you feel super happy. And I'm simply saying predict how serotonin would react with a base, OH minus, and an acid, H plus. So we need to think, which is the most acidic site? It's going to be an H that's attached to a heteroatom. And we have OH, NH, and NH2. All of those have electronegative atoms attached. Which will best stabilize a negative charge? The answer to that is oxygen. Oxygen is really happy with a negative charge because it's the most electronegative. The most electronegative atom wants a negative charge, and it wants to keep that negative charge as well. So if we treated serotonin with a base, it would come in, it would take the H, and it would generate O minus. So that would give us a base that we've protonated, and drawing just a partial structure there, O minus. This is a really good way of activating alcohols, because actually once you've done this to an alcohol and put a negative charge onto it, it's now more reactive than either of those amines as a nucleophile. So this is a way, using a base, that you can begin to make your alcohols more reactive. We said before that OHs don't react very well as nucleophiles. This improves their reactivity actually. Now, which is the most basic site? Is it an oxygen with a lone pair or a nitrogen with a lone pair? Well, both have lone pairs. Which lone pair is most available to form a bond? Well, it's the nitrogen lone pair, and that's because it's less electronegative. And that means it can be donated. And which would we choose? Would we choose the NH that's here or the NH2 that's there? Well, we need to think about those lone pairs very carefully. If we look at this lone pair, it's actually in resonance with these double bonds. So the NH is in resonance, so it's spread out, and that makes it less basic. So in this case, the NH2 is more basic because it's not being shared by resonance. And so let's just draw out the curly arrows. That means NH2 would donate its lone pair towards that positive charge. And what that would give us, again drawing a partial structure, is NH3 plus. So we can predict simple acidities and basicities based on the same arguments about electronegativities, about how localized the charge is, and about resonance stabilization. Once we can do all these things, we can begin to work out complex reactions. So this was a really important screencast that set all the foundations that we need to now look at a completely unknown reaction and work it out. And that is what we'll be doing in the next screencast.